Start recording. Look for my chat window. There it is. How is everybody today?
Doing good, Professor.
Good. Tired. Elizabeth's tired. I'm kind of tired too. Put some thumbs up. That's good. People are still adding. I'm going to turn off the music now. Anybody want to guess who that was? And I don't have a good reason for playing this person. But anybody want to guess who we were listening to? The composer? Nobody? No guesses? No, that's all right. We were listening to Cantata Number 2 by Johann Sebastian Bach. No real motivation for me to play that, other than I think it's very pretty. So what do we need to do today? I've got some announcements, I think. Let me try to find my pencil here. And we got some math to talk about. Anybody have any news or anything that they want to share with any other folks in the class? Anything interesting happening, quote unquote, on campus or at school?
The Lakers are in the NBA Finals.
The Lakers are in the NBA Finals. Cool. It's good to keep up with sports, keep up with normalcy. Anybody know anything about the baseball playoffs? Anybody who knows who's in that? I think the Angels didn't make it, but the Dodgers are in, aren't they?
Yeah, and somehow the Astros made the postseason with a losing record. Cheaters never prosper. Just remember that.
Yeah, you're still holding that against them, huh? I think, as rightly so. That was not good.
Isn't it the right of the people who are just to hold it over the people who are unjust? I feel like that's just my position. But yeah,
I think that's very reasonable. I get behind that. Anything else that's happening? I can't think of anything else that's happening this week. Right, the campus has got these candidates for people who want to take the job of provost. That continues this week. So if you get a chance to listen to those candidates in an open forum and give the university your feedback, I'm sure the president will appreciate it. I think there's somebody here tomorrow and somebody here Wednesday. So Wednesday, that'll cut our class meeting a little short, and I'll send out a Canvas announcement about that. I think we'll plan to start talking at 11 o'clock like we did last week. Yeah, I think that's the big news. Everybody knows that we're largely going to be virtual in the spring too. I think I might have shared that. That was announced a couple weeks ago. Yeah, what else? I think that's it. Cynthia, do you have anything you want to share with folks?
Just if we do the meeting at 11 on Wednesday, I'll be here at 10 for any questions for anyone.
Oh, great. It looked like that worked out pretty well last week. Yeah, Niana, you were there.
yes, I was.
I still have to get you some example problems. Yeah.
Also,
Yes.
I was having a problem accessing the quizzes this morning.
Yeah, so I noticed that too. So that leads me to the first thing I want to share. So let me share my iPad screen. So it was my understanding that all got fixed. And, I sent out an announcement this morning saying that. But they don't seem to be quite fixed. And I was just having some problems. Like I would try to click on some to get a quiz and it would let me, right? I could put my name in and it would give me the URL for the quiz. That worked for 3 of them, but for all the rest, when I click it, it was like having me edit the form. So that was driving me crazy. So
Yeah.
if you
I was having issues opening it, and then when I was going to try to submit it, it said that I had access denied.
Oh, on the the Canvas quiz thing itself, huh?
Hmm.
Now that I can fix. Let me do that right now. So okay, those are open, but I'll maybe I need to set the date. I'll look at that when we take a break, Yanni, but thanks for giving me that additional information.
Thank you.
So you bet. Thank you. So this is what I want you all to know, that I don't want this technology crap to slow you down. So if you want to take a quiz, email me and I'll email you a PDF of the quiz. And then you can submit it to the Canvas assignment when you're done. Yeah, and after class today, I'll continue working on this Google form stuff, see if I can fix it. Okay, so if you want a quiz, email me. All right, and then you start the quiz whenever you want to, because I'm not going to probably get it to you immediately. You could also text me. That might be a more immediate way to do it. But contact me electronically and I'll email it to you. But right after we get out of class, I'm going to go work on this because it's important to me that works and allows you to take the quizzes when you're ready and when you want. All this other crap is slowing us down. So there's that. Okay, so I think that's the operational thing. And I still have a bunch of learning target quizzes I need to grade. So that's on my list too. So, I was going to show you. So I was all happy about this before we learned it didn't quite work out. But I'm going to show you my web browser here in a second. Let me do it now. So I'm on our Canvas site. Actually, it's not ours. Let's go to ours. So I'm going to go to the learning target quiz page. So once I get this all worked out, you'll see that I've added a bunch more quizzes. Right, so a bunch of alternate stuff for the learning targets we've been working on, or we've finished a while ago, and then a bunch for the limit learning target quizzes. And soon I'll add more for the derivative, the stuff we're going to start today, the derivative learning targets. So these are there. It's these PDF links right here that aren't quite working. And then Niani says that I need to look at these links for the Canvas assignments where you turn them into, but I'll look at those links when we take a break today, hopefully get that working right away. And then these are the PDF links. I gotta figure that out. But there's a potential for you to grab a bunch more quizzes and make progress on those. All right, are there any, another thing. So before I ask you if there's anything that you all want to talk about, let me show you another page. I'm going to go to the page that has links to our course material. And down at the bottom, I added 2 screencasts. One screencast is on the continuity theorems. We talked about those last time. This screencast just repeats a bunch of stuff I told you already, but it also adds in detail about the proofs of the continuity theorems, the pieces of the continuity theorems. So if you want to see how those proofs work, watch the screencast. You'll see that the proofs are pretty straightforward. And yeah, so that's there for you. It's about a 15-minute screencast. And then there's another screencast on rates of change. And this kind of picks up where we ended class last time and kind of gives you an idea of where we're going with functions and how we're going to head into the derivative area. This take on derivatives and rates of change is a little different from the way I'm going to talk about it today. So it complements what we're talking about today. Take a look at it. It's about 12 or 15 minutes as well, if you want to get another look at how we're going to think about and talk about derivatives. All right. So now I'm going to go back to my iPad. I'm going to ask you, are there any questions that you all have about anything we've talked about so far?
had a question.
Yeah.
So regarding the quizzes, we're only allowed to retake one per week, right?
No, actually, you're allowed to take 3 quizzes per week, and that includes a retake. But if you retake, you've got to wait 72 hours before you retake it. So that gives you time to think about mistakes you made, fill in the gaps that that you made, and that's 72 hours after you take the first quiz.
Okay.
So yeah, you can take up to 3 a week, and if that could include retakes.
Okay. Thank
Okay,
you.
you bet. Good question. Any other questions about things? Okay, well, let's talk about math then. So what I want to talk about today is going to lead us into the topic of differentiation. Okay, and differentiation is like a really important, it's like 1/3 of the course. So we're heading into an area that we're going to spend about 3 or 4 weeks on, just talking about differentiation. And here I'm going to try to give you a foundation for understanding what differentiation is, why it's important, and how to connect computation with what's really happening, right? So a good conceptual basis. And a phrase that goes along with differentiation is this: the instantaneous rate of change of a function f of x at an input c. So this is a phrase that gets associated with differentiation. It's kind of synonymous with differentiation. And I want to expose you to it now. And hopefully by the end of our meeting today, you'll have a feeling for what this means. Yeah, but I'm going to lay it out there without telling you what it means, and kind of approach it from a bunch of different directions a little bit at a time, and sort of finally, maybe by the end of the day, you'll have an understanding of what this means, or what kind of meaning we're going to hang on this. All right, so where we are so far in the course conceptually is that we've talked about continuity of a function. Okay, and we've defined what it means at a point, continuity at a point, and we extended that to an interval. But for right now, what it means for us is a function is continuous at a point x equals c if this limit equals f of c. So this tells us something really important about a function. It tells us that the function at x equals c, there isn't a jump, there isn't a gap, there isn't a vertical asymptote. It tells us that the graph of the function comes into the location c comma f of c and passes out of the location c comma f of c nice and smoothly. And last time we met, what I told you is I said, this means one of 3 things happens at c comma f of c. So I'm going to draw 3 pictures here. We know that the graph of the function comes into and goes out of the point c comma f of c nice and smoothly. So that means it could come out from above and down below, or it could come in from below and out above, or it means it could kind of come in and go out at the same level. These are 3 things that could happen. And I just want to point out to you is that all of these 3 things happen, or any one of these 3 things can happen when you have a limit statement like this. And that the limit, let me write this correctly, the limit statement does not distinguish between these. Okay, that is to say, just because we know that this limit is true, we do not know which of these 3 things is really happening. And what I'm going to tell you today will start allowing us to distinguish between these three things. Right, we're going to look at things today a little differently. That's going to give us some more information that will allow us to add to this limit statement and say, hey, this is happening, or this is happening, or this is happening. And so this is a way that we can use, turns out, calculus to understand functions a little bit better. Okay, so before we get to that idea, let me back up and talk about functions for a second. And we know that a function is a rule that assigns to each input exactly one output. That's our definition of a function. And we love to graph functions. So I'm going to show you two functions here. One function is going to take this big interval and map it, and the other function is going to take a small interval and map it. And so in the above picture, assume the x and y scales are the same. So 1 centimeter represents the same number of units on the horizontal axis as it does the vertical axis. So on the first graph, I'm going to have my function, it's going to go like this. Right, and say there's some c in the middle. So notice that this function mapped the big interval to a small interval. So we might say that our function f is compressing the interval, it's squishing it. In the other picture, I draw my function like this. And so it's mapping the small interval to this big interval. And so this might be the case where the function is stretching our input interval. So if you think of the input interval as rubberized, in the right picture, the function is taking the input interval and stretching it out to be longer. And in the left picture, my function is taking the input interval and squishing it down to be shorter. Okay, so it's like all the points on the interval here are being pushed closer together. The inner points on this interval are getting stretched out, spaced out further, okay, to be a longer interval. So this is kind of like a kinematic way of understanding what a function is doing, compressing or stretching out the inputs. Another thing that you can see here is from the picture of the graph is if I take inputs and I make them bigger, well, you can see what they're doing on the graph. They're kind of climbing up the graph. And so if you look at what's happening on the outputs, they're also getting bigger. So here on this left graph, as inputs grow, so do outputs. So my function in this case is preserving the direction of inputs. Okay, grow to grow. Looking at the graph on the right, a similar thing is happening. If I make my inputs bigger, look at what's happening on the graph. They're climbing up the graph, and you can see the outputs are also growing. Contrast that with a graph that looks like this. Right, so if I'm on this interval, and I'm taking two inputs and I'm making them bigger and bigger, well, what's happening to the outputs? Well, the points on the graph are going down to the right. And so the outputs we can see they're also going down. So this over here is an example of function is reversing the direction of the inputs. Okay. So these are other things that a function can do. Compress or stretch, or preserve or reverse the direction. Limits don't let you see what's happening in either of these types of behaviors, but they're behaviors that functions can exhibit. And I'm going to show you that this new idea of derivative is going to let us see what, shine some light on these two properties of functions. All right, so is there anybody have any questions on this, what I'm talking about here? Compressing, stretching, reversing, preserving.
Yeah, quick question in terms of if you compress the y-axis, does that mean that you're going to be stretching the x-axis and vice versa? Or no?
Well, that's an interesting observation because it is relative, right? So in if this left picture, right, you're looking as the x's are the inputs and then the y's are the outputs, and here you're compressing. But it's easy to look backward, right? And see, oh, well, if I go backward, then I'm taking a smaller interval and making it become a bigger interval. So if the function is invertible, then the inverse function would have a stretching behavior, right? Likewise, if your function stretches, the inverse function would have a compressing behavior. So those ideas kind of go hand in hand, Yanni. Does that answer your question?
How would we know if the function would be invertible?
If the graph passes the horizontal line test.
Okay.
Okay, good question.
Thank you.
Yep, you're welcome. Okay, so let me move on to the next idea here. And this next idea is going to help us understand, get closer to understanding how we can tell when a function is doing one of these things. So this next idea is local linearity. All right, so this is what I want to tell you about local linearity. So local means nearby. And linearity means like a line. Oop. Okay, or maybe not like, we'll say is a line. So what we're going to talk about is we're going to have a graph of a function, and we're going to have it at some point. And we're going to ask the question, is the function locally linear at x equals c? That is to say, near c here, near this point on the graph, is my function like a line? Okay. Later, we're going to learn that a function is differentiable at x equals c if its graph is locally linear at x equals c. Okay, so this is going to be a fact we'll learn more about later. But the idea I'm about to show you is going to explain why this fact is true. And once you see what a derivative is, you'll say, oh yeah, I see it now. Okay, you're not going to see it quite yet, but let me explain this idea of locally linear. Okay. So if a function is nice, and smooth, it's going to be locally linear. And so it means if I zoom into a point where a function is locally linear, if I zoom in far enough, the graph is going to look like a line. Okay. So let's do this for a function. I mean, one of our favorite functions that's not a line, a line is our favorite function. one of our most favorite functions. It's the squaring function. And let's say at x equals 1. So the squaring function, its graph is a parabola. So when x equals 1, the output is 1. This is a cartoon of the parabola. So I claim that if we zoom in around this point, the graph of the parabola is going to get less and less straight and look more and more like a line. So let's look at this. I'm going to pull up Wolfram Alpha, and we'll just go and see if this is really happening. All right, so let me go make sure my browser is here. Yep, my browser's there. Oh, there's even a tab with Wolfram Alpha. So let's share that browser. So I'm here at Wolfram Alpha. I've actually zoomed in to Wolfram Alpha, and let's plot y equals x squared on the interval from 0 to 2. Okay, so x equals 1 is right in the middle of that. But let's make sure that we're using the syntax right. We know what this graph should look like. It should be a parabola. Yep, there we go. There's our graph. So here's our input x equals 1, and we can use the crosshairs and verify. Yep, looks like it goes to the point 1, 1. So now I want to zoom into that point 1, 1. So I'm going to make a progression of smaller and smaller intervals. And first I'm going to start easy. We're going to go to 1/2, or from 1/2 to 1.5. All right. So I'm zoomed in closer. You can still see there's some bend here. Let's zoom in a little farther. We'll go from 0.1 to 1.1. Oh, what happened? Oh, yeah, that's right. 0.1 to 1.1. Is that what I wanted? No, 0.9. I want to go 0.9 to 1.1. All right. There we go. So 1 is again in the midpoint of my interval. See the 0.1 there. And that graph looks a lot straighter. That's because I'm zooming in. But I can zoom in a little further. Let's go from 0.99 to 1.01. So we're zoomed way in there. Okay. So there we go. Now what I want to do, so this is the line. Let's find the equation of this line. If this is indeed a line, we can find an equation of the line. So the form that we're going to use, we're going to prefer when we're doing calculus, is the point slope form. So that's the formula that looks like y minus y naught equals m times the quantity x minus x naught. And I'll write this down in a second where you can see it. So we are going through the point 1, 1. So that's going to be our x naught, y naught. I need to calculate a slope. So I need to find another point that's on this line. So I'm going to come over here to 1.005. I'm going to try to estimate what the y value is here with the crosshairs. And it looks like 1.01 is the output that goes along with that. So the other point on this line here is going to be the point 1.005 and 1.01. So I want everybody to calculate the slope of this line. All right, the slope of the line we see here goes through the point 1, 1 and the point 1.005, 1.01. Calculate its slope. And then we'll play 3, 2, 1, go. So after you calculate the slope, I'll ask everybody to submit it to the chat at the same time. So while you're calculating, I'm going to share my iPad so I can write this stuff down so everybody can see it, see what we're doing. All right, so y minus y naught equals m times x minus x naught. We want to find this formula. And x naught, y naught is 1, 1. So we want m. And we're going to use 1, 1 and 1.005, 1.01 to calculate the slope. All right, are people ready to share what they calculated? You should have had enough time. Type it in the chat, and then I'm going to have you hit enter in a second. 3, 2, 1, go. Okay, got a few people. Yes, so looking in the chat, you know, everybody should be doing this, right? Everybody should take a crack at it. Looking in the chat, the number 2 is the dominant number, right? And that's the right number. So looking at my iPad, we know that the slope is rise over run, the change in the y over the change in the x. So if I use that to write this down, the difference in my y values divided by the differences in my x values, making sure to keep the order the same, then I get 0.01 over 0.005, and that's 2. Right? If you want, you can move the decimal place over 3 in the denominator. That means you can move it over 3 in the numerator. So you get 10 over 5, and that's 2. So the slope is 2. All right, so that means that our equation is y minus 1 equals 2 times x minus 1. So y equals 2 times x minus 1 plus 1. So I'm going to go back to Wolfram alpha. And I'm going to add to this plot the plot of this line. And y equals 2 times x minus 1 plus 1. Right? All right, getting rid of the typos. So I'm going to graph the parabola and this line, this local representation, or what the parabola looks like locally at 1.1. So hit return. Wolfram alpha is going to, this verifies that it's doing what we want it to do. And here we look at the plot. Down in the right-hand corner, you'll see that Wolfram alpha is saying, yep, I'm going to draw 2 things, your squaring function and this other line. Then you look at the plot and you only see one thing. Well, that's because they're overlaid with one another, right? You can kind of see that this is colored, maybe a purple, this combination of the blue and the red. So they look like they're the same thing right here, which is exactly what we thought would happen, right? If a function is locally linear, it means if you zoom in, it's going to be a line. This picture shows us that this is the correct formula for that line that we see here. But now what I want to do is I want to back out. Let's zoom out a little bit. So we're going to go from graph this from 0.9 to 1.1. And you see here, it's still close, but at the ends, you see they start getting further apart. You see the blue that has a little curve into it, and the red definitely doesn't, or the purple definitely doesn't have any curve. It's a straight line. So you see here, the blue curve is gently curving away. Let's back out a little bit more. So we're going to go from 0.5 to 1.5. Okay. There you can see the curve in the parabola and compared with the straightness of that line, that local line. And then I'm just going to do one more, go from 0 to 2. And that curve, you'll see the curve gets more distinct. Okay. So here's a picture of the parabola, the squaring function, along with the local line at 1.1. So this line is really important. It's important to our understanding of the squaring function, actually. This line is what's called a tangent line at 1. So I'm going to switch back to my iPad. You can do it. All right. So back here down in the bottom left, my little cartoon, we just drew in this local linearity line. And I'm telling you that this line is called the tangent line to the graph at x equals 1. And this is a really important line for us. And we're going to invest a lot of time to figure out what the tangent lines to functions are. In particular, we're going to be really interested in the slope of this tangent line. It's easy to find this x naught and y naught because it's kind of part of our assumption, but the work we'll do is to estimate the slope, and it's the slope of this tangent line that's going to be really interesting to us. So let's do this for another function. Anybody have a function that is nice and smooth that we can do this analysis to? Throw it in chat if there's a function you'd like to see this done with. Anybody have a favorite function? Nobody? The only rule is it can't be the squaring function and it can't be a line. All right, Cyrus, thank you for playing. We're going to do the sine function. Okay, sine function, perfectly good function, great, important function. Jnani, I'll talk about x cubed in a minute, actually. I'm glad you bring it up. So let's see, let's look at the sine function at x equals pi over 4. Okay, because then we know that pi over 4 comma root 2 over 2 is on the graph of the sine function. And let's ask, is the sine function locally linear there? At this input? And if so, what is the tangent line? We'll find the tangent line. Okay, so let's go over to Wolfram Alpha. I'm going to switch back to my browser. And we're going to play this game again, but with the sine function. And so let's type in y equals sine of x. And we're going to go on the interval from 0 to pi over 2, because that has pi over 4 right in the midpoint. So there we go. There's the graph of the sine function on that interval. Pi over 4, right? Pi is 3.1, so pi over 4 is just below 1, so it's probably like right around here. Let's zoom in on that point. So I'm going to play this game. Pi over 4 minus 0.5 to pi over 4 plus 0.5. So we're going to zoom in on that interval of length 1. Okay, so you can still see some bend there. So let's zoom in on this interval, plus or minus 0.1. All right, so there we are on that interval. Still can see a slight bend, so let's make it even smaller. All right, that looks pretty straight. So let's work on this interval. So we want to find an equation for this line. So we're going to use the point slope form. And so I'm going to write that down on my iPad. And then I'll switch you over to the iPad in a second. But that's y minus y naught equals m times x minus x naught. And in this case, we're interested in x naught comma y naught being the point, pi over 4 comma root 2 over 2. All right, so let me take a second and I'll give you the decimal approximation for that. So the decimal approximation for pi over 4, say that's 0.785. And the decimal approximation for the square root of 2 over 2, let's say that's 0.707. Okay, so 7.85, that's right about here. So we should be coming up to about 7.07. And you can look on the left axis, 1, 2, 3, 4, 5, and you can see that the height of my crosshairs here looks like it's just below where the graph would be saying 0.707. So we're pretty good, but maybe we could do a little bit better. So let's find another point that's on the graph of this function. So let's go here to 0.790. 0.790. What's the y value that goes along with the y value of the graph there? It looks like we're just a little bit above 0.710. And it looks like each one of these tick marks is about 0.001. So let's say that's 0.7105. It's a little bit below that, but let's say it's 0.7105. So what I want you to do is that I want you to find the slope of this line. Okay, so it's the line that goes to the point 0.785, 0.707, and the point 0.790, 0.7105. I just wrote that on my iPad. I'm going to switch over to my iPad so you can see it, but I want everybody in class to use those 2 points and calculate slope. Okay, right here. So pull out your favorite calculator and calculate that slope. And then we'll play the 3, 2, 1 game. I'll give you a minute to do that. And I'm going to pull up my favorite calculator and do the same thing. When you get a number, throw a thumbs up into the Zoom using your reactions button at the bottom of your gallery. Yeah, there we go, Eduardo. See that you got it, Cyrus J. When I see enough thumbs up there, then we can start sharing. Elizabeth, I see your thumb. That's great. Alejandra. All right, that's enough people have given me thumbs up. So I want everybody to take the number that they calculated, throw it in the chat. And then when I say go, hit return, right? 5, 4, 3, 2, 1, go. Yeah, good. Yeah, Cyrus, looks like you are off by a factor of 2. I don't know how that happened, but the answer I get is 0.7. Let me, yeah, maybe you all saw my iPad screen. Yeah, 0.7.
Yeah, no, I just realized I just flipped my X's and Y's in the equation.
Ah, interesting. Okay, so the equation of our tangent line is going to be y minus root 2 over 2 equals 0.7 times x minus pi over 4. I'm going back to the exact numbers and not doing the approximations just because we know what the exact number should be. So that's going to be y equals 0.7 times x minus pi over 4 plus root 2 over 2. So let's throw that back into Wolfram Alpha. So I'm sharing Wolfram Alpha with you right now. I'm going to add in the equation of our tangent line. So, and y equals 0.7 times x minus pi over 4 plus the square root of 2 over 2. And we'll just look at that on the whole interval from 0 to pi over 2. Okay, and hopefully it'll look right. Okay, so there we see both graphs, the graph of the sine function and the graph of the line whose formula we calculated together. So tell me in the chat, yes or no. Does this look right? Does that purple line look like what I was calling a tangent line? 3, 2, 1 game, right? Yes or no, Y or N, into the chat now. Does this look right? 3, 2, 1, go. Yeah, it does look right. This does look like a tangent line. This does look like a tangent line. If you want to be convinced, we can play this game where we zoom in a little bit more. So pi over 4 minus 0.25 to pi over 4 plus 0.25. So zoom in on pi over 4, and you can see this tangent line, it's looking like the graph of my sine function. Let's zoom in a little bit more. Is our line lying on top? Looks like it wants to lie on top of that sine graph. So I'm convinced. Zoom into a smaller interval. Sure enough, it looks like that line sits right on top of that sine function, that sine graph. Looks like that line is the local linearization of the sine function. Yeah, looks like we were right. So I'll talk a little bit about how to recognize a line and see if it's a tangent line or not in a minute. But this is a good tangent line. This is what we want to see. Okay. So working here, like we did with the squaring function and working here with the sine function, this process shows you how you can come up with the equation of a tangent line to a function. So we're going to spend the next couple of weeks talking about tangent lines and their slopes and talking about how to calculate tangent lines and stuff. What we just did today, right? We just did right now is a way to find a tangent line. Okay, by zooming in and looking at that sort of what the function looks like up close and blowing that line up, right? So the tangent line is really what the function is doing. It's really like the local linearization of the function. So this is a deep and important idea. Any questions about this? You good with this, Cameron?
Yeah, I'm good with
Okay. Rihanna, does this make sense?
Yes.
Okay. So let me now change tack a little bit. We're going to go back and talk about. Oh, wait a second. It's about time for a break. Why don't we take a break, and then when we get back, I'll talk about how to draw tangent lines. What should we be looking for in a tangent line? Why is this a good example of a tangent line? What we just looked at in Wolfram Alpha. But I'm going to turn the music on for 5 minutes. We'll chill out, and I'm going to go and look to see what's wrong with these Canvas assignments. Okay. So see you back here in 5 minutes. Yeah. Come in. Yeah. Come on. Come on. Come on. You close the door.
She's like, ooh, what can I? She's like checking everything out.
All right, my timer's going off. 5 minutes is up. Ugh, my dog is being a pain. Yeah, I'm talking about you. Yeah, I'm talking about you. All right, pause and music. Okay. All right, so I went to look at the learning target quizzes on Canvas, how you turn them in, and they look okay to me. But they look like they're available. So if you're having problems with them, let me know. So the next thing I need to look at is downloading or getting the quizzes themselves. Until I have that figured out, just email me or text me and I'll message you a PDF of the quiz. Okay. Yeah, thanks, Danny, for looking into it. Let's go back to my iPad. Let's talk about tangent lines. And how to sketch them. We'll have an activity in class on Wednesday, I think, about sketching tangent lines. So I want you to practice this before we have class on Wednesday. So we've seen 2 examples of tangent lines, and I've sketched a cartoon of a tangent line. If you're trying to figure out what the tangent line is to a graph like this at this red point, this red dot, that's what a tangent line would look like. All right, so here's a cartoon of what a tangent line looks like. So in general, but not always, tangent lines have the following properties. Touch the graph at one point and don't cross the graph when they touch. Okay. In general, this is what tangent lines look like. And I will show you some important exceptions to number 2. So just like put a little asterisk there. All right, so we'll come back and we'll talk about a couple important exceptions to number 2. But in general, this is the way you should be thinking about them. So here's, oops, 2 things that tangent lines do not do. So a tangent line will never look like this. Okay, it doesn't look like that. That's called a transverse line, not a tangent line. Okay, this picture here that I just drew is very different from this picture. People might be old-fashioned, like to say a tangent line kisses the line. Okay, a tangent line gets closer and closer to the curve, and then touches it, and then starts moving away. It just kisses the line at a point. This picture down here, this line, this transverse line is punching through the graph. Okay, it's punching through. It's not kissing. It's not approaching it gently and then moving away. It's punching through. So this picture down here is not a tangent line. So I'll draw a tangent line again, just to demonstrate how I do it. So here's a curve. You want the tangent line at that point. What I tend to do is you can't see my pen, my Apple Pencil, but I put my pencil right at the point, and then I draw the tangent line away from that. Right, I try to draw that part of the tangent line that kisses it, and then I return my pen to the point, and then I draw the other half. And with enough practice, usually those 2 halves look like they line up pretty well. But that's how I draw a tangent line. And the idea is that the tangent line and the function are getting closer and closer and closer together. Okay, that's how you want to draw it. And that's this idea of the tangent line comes and it kisses the graph and then moves away. Let's talk about the exception to this case 2 here. So what's an exception? An exception is like the graph of y equals x cubed. The graph y equals x cubed, so I'm going to draw this a little fatter. No. The graph looks like this. And so if you want to talk about the tangent line here, it turns out the tangent line is coincident with the x-axis. And this is an example of where the tangent line does cross the graph of the function. Okay, let me redraw this because using. Okay, so the tangent line can draw the graph, or can cross the graph of the function. But this tangent line has all the properties we want it to, right? It's getting closer and closer to the graph, to the point and to the graph at the same time. And then it slowly gets further and further away. Okay, it just so happens that something's happening with the graph of the function that makes it cross. And what we'll learn later is that the graph of x cubed to the right of the point of tangency here, the graph is concave up. And on the other side, it's concave down. Okay, and this turns out to be what's called an inflection point. So they're easy to spot. You know when this stuff is going to happen. And we know it's going to be rare, but it can happen. And let me show you another example of where it happens. And we'll go with Nyani's, not Nyani, Cyrus brought this up, the sine function. So the graph of the sine function looks like this. And it turns out that is an inflection point, and so is this, and so is this. But at that inflection point, the tangent line looks like that. So it's an example of a function where there's a change in concavity, and so the graph crosses, the tangent line crosses the graph. So going back, these two properties are important properties, and they're good touchstones for 99% of the tangent lines you'll ever draw. You just need to know that there's some times when they do cross the graph, and that happens at what we'll later call an inflection point. Let me say something about number one. The tangent lines always touch the graph at a point here. They touch the graph at one point, that point of tangency. Let me write that down here. Point of tangency. But they could also cross the graph at another point far away. Having a tangent line is a local property. And so anything we talk about with regard to tangent lines and stuff is really about near that point of tangency. So something crazy could be happening down here. Something crazy could be happening up here. Right? A tangent line will only touch the graph at a point, at one point near that point of tangency, or that is that point will be the point of tangency. But if we look back at the sine function, and I'll use a different color here. We'll use blue. So consider this point. And if you take a look at it for a second and imagine what the tangent line looks like. Can you see the tangent line? I'll draw it in orange. So the tangent line only intersects the sine curve locally near that blue point. But can you see where it intersects the sine at another point? Can you visualize it? Let me draw it for you. So I'm putting my pen tip here on the point of tangency. I'm going to sketch the tangent line on one half. I'm going to sketch it on the other half, and I'm going to extend it. So here you can see there's another point of intersection of the tangent line with the graph of the function. And I'm telling you that's okay. That will happen. A lot of times that will happen. When we say a tangent line only intersects the graph once, that's locally. That's this point of tangency. One thing we're going to talk about today are secant lines. If I've got a function like this, and I'm interested in a tangent line at a point, right? So here's a tangent line. If I make a mistake and don't get that angle right, I might draw this line. And this red line here is what's called a secant line. And it's the secant through, in this case, c comma f of c and c plus delta x comma f of c plus delta x. Okay. You might call this number b instead, and it makes it easier to write down that second coordinate. But if a line crosses a graph twice, you can talk about it as being a secant line. Okay. And I'll say some more about that. So don't accidentally draw a secant line when you're looking for a tangent line. That's the point I'm trying to make. Don't accidentally draw a secant line when you're trying to draw a tangent line. Okay, so that's how to draw a that's how to draw a tangent line. But there's one more thing I want to say about it. When we sketch a tangent line, often our goal is to find its formula. Okay, so when we're sketching a tangent line, often the reason we're sketching it is to find the formula. The formula we'll prefer, or we will favor, is a formula in the point slope form. You should be familiar with that. And to find the things to put in to the point slope form, the x naught and the y naught, these are generally easy, right? Because you can look at the graph and you can see that point that your tangent line, or that point of tangency, the coordinates of the point of tangency. Finding the slope takes a little work. It's not as obvious as the coordinates of the point of tangency, but let me just remind you how to find the slope. And the slope is the most important thing. Okay, the slope is going to be the most important thing for us in this class. So what I'm going to do here is I'm going to draw coordinate axes. And I'm putting ticks on there so you can see what the measurements are, the unit measurements, the distance measurements, okay? Because we need those when we're going to estimate slope. And let me draw a graph of a function here. Let's say it's like this. And let's say I'm interested in estimating the slope of the tangent line at that point. So there's the point of tangency. So the first thing you do is you want to sketch in that tangent line. And so I'm going to extend it. So we ask, what's the slope? So here's how you do it. You always remember slope is rise over run, right? Rise over run. Okay. So you want to find a triangle, a right triangle, so you can estimate the rise over run. So let me use gray here. And so what I like to do is I like to pick a starting place. So here it's going to be x equals 3, and I'm going to pick an ending place. So it looks like x equals 9. Okay, so I'm going to find out, go up to see the graph or the point on the tangent line, just like I did over on the left. And then I'm going to go see what their y coordinates are. So I've got, my pencil stopped working. So look for estimate the y coordinates of these 2 points. Looks like I'm hosed here. Let's take a break for half a second while I try to find a substitute for my stylus. So I'm going to redraw this picture here while my stylus charges up again. Hopefully it'll just take a minute just to get enough charge. And so what I'm going to do is just good old fashioned pencil and paper. Just need to get this camera lined up okay. Get a little light on it. So what I'm trying to do here so I'll just redo this. And I think I had a graph that went like this, and I said, hey, let's estimate the slope of the line that's tangent at that point at 5,2, it looks like. So if I were to sketch the tangent line, that's not that great. It's good enough. We're just drawing cartoons. So here's my sketch of the tangent line. What I said is I would pick some input, some x. So I'm going to come down as far as I can. So let's come here to x equals 2. So there's the point on the graph. And I'm going to come up as far as I can on the x-axis and go as far as I can. And then what I'm going to do is I'm going to use a ruler here so I can get a good estimate. I'm going to go figure out what the y coordinates of my points are. So having the ruler here is good because this is where the estimation work is going to take place. I had leeway to choose my x coordinates. Okay, I got to choose 2. I got to choose 9. Okay, so I got to see that my change in the x's here is 7. Right? Yeah, 7. But now the tangent line gets to dictate what these y values are. So I just need to listen. I need to pay attention. So using this straight edge, I figure out what the y values are. So over here, I'm going to say this looks like it's about 0.3. And the y coordinate of this point looks like I'm going to say it's 4.8. 4.8, yeah, 4.8. So my cartoon here, my estimates say that this looks like it's about 4.5. Okay. So as my x's increase, so delta x is positive, my y values are increasing. So it looks like my y values are 4.5, positive 4.5. So my slope, delta y over delta x, is change in y, 4.5 over 7. All right, so that's my estimate for the slope of this line. If I want to make it a little nicer, I could double the top and double the bottom, 9/14. And then if you wanted to figure out a decimal approximation for that, that would be reasonable too. So my point in doing this example for you is that if you sketch a tangent line, you can estimate its slope and you can get a reasonable approximation for its equation, just like we were doing with Wolfram alpha. Okay, so you get a reasonable equation, a reasonable estimation of the equation line for your tangent, the equation for your tangent line. Okay. And this will be important for the exercise that we do as a class on Wednesday. Okay. Any questions about that? And let me just repeat, when you estimate the slope of a tangent line, you really need to take into account what the measurements are on your horizontal axis and what your measurements are on your vertical axis. Okay. And it wouldn't hurt to remember that delta x is the new value minus the old value of x, and delta y is the new value of y minus the old value of y. Because the signs of these deltas are important. It makes a difference between whether or not your line has a positive slope or whether it has a negative slope. Okay. So let me think. What's the next thing I want to talk? Oh, the next thing I want to talk to you about is instantaneous rate of change and average rate of change. I'd like to see if my stylus is working. Take a moment and see if it will scribble. Nope. So we'll continue with pen and paper. And I'll add these onto the PDF of the lecture notes. So instantaneous rate of change. Okay, so let me ask, can anybody give me an example of a rate in chat? Can somebody throw me an example in chat of a rate? Cameron says speed. Yeah, like you're driving a car, right? That kind of speed. And a speedometer gives you a measurement of your speed. And so if you're driving an American car, your measurement of your speed might be miles per hour. Okay. So what I want to point out to you is miles per hour really is a fraction. So it's a number of miles divided by a number of hours. Okay. So this is a property that all rates have. All rates are measured in units that are fractions like this. So I've got a cup of coffee here on my desk. It's pretty empty. As I drank more of it, it got colder and colder. So we could also measure a rate of temperature change. And so that unit might have degrees per minute as its unit. Okay. So when we talk about instantaneous rates of change, and we talk about what I want you to do is I want you to connect the idea of rates to this, right? And actually, these are actually units on rates of change, right? My coffee is getting colder and colder. How fast is it getting colder? Well, we measure that in these degrees per minute. Your car is moving quickly. How quickly are you measuring it? Or it's changing position fast, right? How are you measuring that change? Well, in miles per hour. When I've got a graph of a function, and the function has certain input units and it has output units, and then I ask about the tangent line, well, the slope of the tangent line is its rise over run. So the slope is the change in y over the change in x. And it's measured, its units are a ratio of the output units to the input units. So the unit on slope is a rate of change. Change because of the deltas, right? The change in y values over change in x values. But this idea that it's a ratio of units means that the unit on a slope of on a tangent line is a rate of change. So average rate of change Okay, this is a technical term. If I've got a function at one point A, one input, it's got a value, and another point B, it's got another value. I can talk about the average rate of change of f of x on the interval from A to B. And it's delta y over delta x. The literal delta y over the literal delta x. Okay, and delta's in terms of my functions. So this is what we define an average rate of change to be. Okay? And it has the units of rate of change, right? You've got the units on the input and the units on the output. Okay? But this is the formula for the average rate of change of a function. What we want to understand is the instantaneous rate of change of a function at an input. Okay. And notice the problem that creates is that if you're at an input, that forces you to divide by 0. Okay. And I know I'm toward the bottom of the page here. Let me move that up. So that's a problem. We don't like division by 0. But I'm going to show you how we get from here to something that gives us this instantaneous rate of change. And I'll point out that when we talk about average rate of change, we're talking about average over a whole interval. And instantaneous rate of change is, what if I shrink this interval down to be smaller and smaller and smaller? And if you think about that for a little while, you'll understand that's exactly a statement about limits. Okay. So let me start a new page here. Geometrically, an average rate of change is the slope of the secant line. See if I can draw this. So an average rate of change is the slope of that secant line. Now, what we want to be able to do, and I'm looking to see if I've got another colored pen over here. I don't think I do. Let me take a pencil. Hopefully that'll show up okay. What we want to do is say, how do we get this instantaneous rate of change? How do we get the slope? Yeah. And so what we're going to do is that we're going to just keep calculating the secant lines or the slopes of the secant lines, but we're going to make B closer and closer to A. So if I move B to the left, that shoves this upper point down, and it's going to get closer and closer to that point. Symbolically, this is the limit as B goes to A of f of B minus f of A over B minus A. And this is exactly the instantaneous rate of change when that limit exists. Alternatively, if you think of this distance between A and B here as delta x, so delta x is B minus A. So B is A plus delta x. Then this formula can be written as the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x. The denominator simplifies to delta x. And this is how we're going to define the instantaneous rate of change. In this case, it's at x equals a. All of these numbers are average rates of change. And so the instantaneous rate of change is a limit of average rates of change. All right. So I think what I'm going to do, since my technology is not agreeing with me, I think I'm going to just stop here and maybe make a screencast that will, once things get charged, that will fill in from here to where I wanted to end up. But we're pretty close. Yeah, we're pretty close. But I'll make a screencast that talks about instantaneous rate of change and average rate of change and put it out there. But this is the main idea, that when we calculate the slope of a tangent line, we're going to be thinking of them, those slopes, as limits of expressions like this, limits of secant, slopes of secant lines. Yeah, so I'll post a screencast soon after I get the learning target quiz stuff figured out. And that'll give you a couple examples of how we do this. And then what we'll do in class on Wednesday is we'll do an exercise in groups where I'll give you a graph of a function, and then you'll have to estimate some tangent lines, slopes of tangent lines to those graphs, and we'll pull those together in an interesting way. Okay, so sorry about the technology mishap. This hasn't happened to me before. It's just comes as a surprise. I'm trying not to let it happen again. But yeah, so let's call it a day. Thanks, everybody.
Professor, also just to let you know,
Yeah.
I was trying to log in and I wasn't having success. It's saying I need permission for both the submitting link as well as the link to open the individual quizzes themselves.
Huh.
So
Okay. What quiz were you trying to do, Niani?
I was doing L3.
Okay. Yeah. Okay. So there's just one L3A. Okay. And submission.
Though if I were to try to click on some of the other ones, even for the previous submission, it's still saying that I need permission.
Yeah. Okay. I may send you an email about it just to follow up on it, but thanks for helping me figure out and see what's going on from your end.
Of course, no problem. Glad to help.
Yeah. Okay. All right. Thanks, everybody. I will see you on Wednesday. We'll start late. You'll see a message about it, but Cynthia's going to be here at the normal time at 10 to answer questions about stuff we've been talking about and that sort of thing. So plan to show up at 10 and hang out with Cynthia and do some work with other folks or take learning target quizzes. And then we'll start formally a class at 11. That's the plan. Okay, that's it.
Dr. Miller?
Yeah.
I had a quick question regarding the learning target quizzes.
Yeah.